Hello everyone, welcome to Ask Seminar series. I'm John, the seminar coordinator, and I will be today's moderator with Ms. Kathy Medney. Kathy is our communication specialist. And today our Associate Director, Ralph Ferrero, also join us, and Ralph will be introducing the speaker before he gets started. And just so you know that the seminar is being recorded, and we will publish the recording on our YouTube channel. Please feel free to check it out. It usually takes a couple of days. And today is our last seminar this semester before the Christmas. So I hope you enjoy the seminar and have a nice holiday. And our seminar will be resuming in January next year, so please stay tuned. And today we have our speaker joining us from the Columbia University. Before he gets started, I'm going to turn this over to Ralph. So Ralph, please go ahead.
Yes, thanks, John. I wanted to just say thanks, John and Kazi, for a great semester of talks, and we look forward to next semester. And so today's speakers, Professor Pierre Gentine, Columbia University. As John mentioned, I have a feeling it's going to be our largest seminar in a virtual sense, and I think it's appropriate based on the topic here, machine learning, and really intrigued by his talk. I like the notion of machine learning back to physics, because I think that's from my perspective, that's always sort of been a bit of a missing piece here. So be glad to hear the talk. So just a little bit of Pierre. He's at Columbia University in the geophysics. He's professor of geophysics in the Department of Earth and Environmental Engineering, and works on terrestrial water and carbon cycle studies. He's won numerous awards, NASA, Department of Energy, NSF, AGU, among other things. He's also director of a Science and Technology Center for machine learning and artificial intelligence. I did a little search. He's got first degree, it was in France, and then his PhD at MIT. And I'm going to turn it over to Pierre, and I'm going to pay close attention to this talk.
Thanks so much, and happy to take any questions at the end. I would like first to acknowledge most of the people that have been actually doing the work. So Sarah Shamek in my group, Kara Lamb as well, and Yu Wang. And collaborators, especially in Germany, Veronika Eyring, Tom Böckler in Switzerland, and Mike Pritchard at UC Irvine, and Nando Iglesias Suarez also in Germany, and Jakob as well, Runge. And the title of this talk is Physics to Machine Learning, as you said, machine learning back to physics. And really, the caption of that is a roller coaster journey to the use of machine learning in climate science, and basically trying to share what has been my experience through that. So getting through the excitement, and then getting through potentially some of the limits that we witnessed when we were trying to apply machine learning to Earth science, and trying to see how we can move forward, potentially as a community, and the more the merrier on that field. And of course, I would like to acknowledge the funding agencies. So the NSF for our Science and Technology Center, LEAP, Schmidt Futures for M² Lines, and the European Research Council for a project called USMI. So just a little bit of background as to where I'm coming from and why I really got interested in using machine learning is that if we look at what we call climate sensitivity, which is the response of the global temperature to a doubling of greenhouse gas concentration, if we look at the response of temperature at the global scale, we typically use a climate model, or a range of them, actually, to start thinking about the change of the global temperature. And we can see that there's actually a substantial amount of spread when we start thinking about when are we going to pass a given threshold in temperature. So if you look here on the y-axis, you have what we call the 2 degrees of threshold, so Celsius here, of the Paris Agreement. And basically, one circle here shows the result from one particular climate model, or we call them an Earth system model these days. And the main take home here is that there's very substantial spread as to when those models are going to project that we are going to pass those 2 degrees of warming of threshold compared to pre-industrial levels. And you have some models, so the more reddish type of models here at the bottom left, that are very conservative or pretty negative, you could say, and they are saying that we are going to pass this threshold by 2035. And you have some models on the top right corner here that are saying, you know what, that's going to be actually way, way further down the road. That's going to be only in 2060, okay? And the main point being here that there's really a substantial range, you know, so if we are, say, a policymaker and you want to start thinking of when we are going to pass this threshold, I mean, you cannot really deal with such a large uncertainty, right? 2035 is almost tomorrow. 2060, that's a couple of decades further down the road. So we could have potentially the time to adjust or to plan and to adapt, right? And you could say, why do we have such a huge amount of uncertainty in terms of the projections that we have? And you could relate that to clouds in particular. So here is just a scatter plot, and we could get into the weeds as to whether that's a causation or not. But the main point being here that there's actually a very strong correlation between that, what we call climate sensitivity, so that response of a climate model to increase to a doubling of carbon dioxide, to low cloud reflectance change. So basically what this means is that you have models that are basically that have more clouds, and those clouds are actually brighter. And those are the ones that will be a little bit more optimistic, right? That they will be the ones that will be saying, you know, that's going to be, a bit optimistic, saying that that's going to be further down the road that we will pass this threshold of 2 degrees, right? So they tend to be on the bottom right. And you have models that tend to have fewer clouds or clouds that are darker, and they tend to be amplifying the feedback, as we call it, the cloud climate feedback. And those models tend to be actually more negative, right? So they tend to be more pessimistic, and they tend to say that, in fact, we are going to pass the 2 degrees of warming pretty soon, right, in 2035. But the main take home here is that we have a substantial amount of uncertainty in the models, and we can relate those uncertainties to basically small processes, in particular clouds, right, that tend to be actually very small. Just look outside. Here is a sunny day today, but you know, every time you see clouds, they are very small in scale. And it's not just a global issue. You could start zooming in, and so that's one example here for the US, and looking at the distribution of rainfall as predicted by different models. And the main point here is that if we look at the standard model, which is the community atmospheric model here depicted in green, we can see that the distribution, so it's really a PDF here, just in log scale here on the y-axis, we can show that the model is actually showing many fewer extremes compared to the observations, which are here in black, right? So in the observations, we see a lot more extremes of precipitation, so very intense rainfall. And the models, as we call them, tend to actually drizzle too much, right? So they tend to have a lot of very frequent precipitation, and those precipitation events tend to be very weak in intensity, so really much more like a drizzle, right? And that must have a pretty strong impact in terms of the water cycle as a whole, right? But basically the main point is that there's quite a bit of a difference between the two. I want to point out that you could run some simulations that are at much finer resolutions. We'll talk about resolution in a minute, but a typical resolution for a climate model is roughly on the order of 100 kilometers to 100 miles in horizontal resolution. And you could run models at a few kilometer scale. And that tends to solve a lot of the issues when we start thinking about the regional hydroclimate and to the regional precipitation. The distributions are almost collapsing here, meaning that, you know, even with the same model, but at higher resolution, we can do a much better job, which is good news. We can go one step further, and then we say that, in fact, those models don't do a great job in terms of predicting precipitation, but you could think about maybe more organize extreme events such as droughts, right? So they tend to happen over a larger spatial range. And you could think maybe there's actually a pretty strong impact, and we could actually be a little bit more prescriptive in terms of what's going to happen next, right? And when you look at that, here at the bottom that's just from the IPCC. So every region here is depicted as a schematic. So that's the Western North America here. This is the Mediterranean here. And basically the main take home is that we don't really know whether most regions of the globe are going to see more or fewer agricultural and ecological droughts. And we cannot say that with confidence, except for the Western North America, so basically California pretty much, and the Mediterranean. And as you know, we've been witnessing a lot of droughts in the past with intense wildfires. So those are regions where we have quite a bit of record, quite a bit of studies showing that there's been historical drying. But for the other regions of the globe, we basically cannot conclude. And so what this means is that in over many regions, we don't know what's coming up next, right? And so how can you actually plan for that? How can you start building, water reservoirs or whatnot if you don't know whether you will be seeing fewer droughts or more droughts, right? So why do we have so many uncertainties, you could say, in those models? Because those are pretty dramatic and they really limit us in terms of tailored climate adaptation. And you could actually get back to your models and you could look at, and I showed you one example here, which was on clouds. And really clouds and small scale processes tend to actually be very difficult to model because they tend to be happening at a scale that's actually much smaller than the typical grid size of an Earth system model, which is here like 100 kilometers. And I just showed you one example here in the tropics when you want to look at clouds, right? You can see it's actually very difficult to actually do that right. We need to actually represent those physical and biological processes in a relatively empirical way. And we call that to parameterize processes, physical and biological processes. And it's not just clouds, it could also be ocean eddy because they are very important in terms of ocean heat content, which is also very important when we want to think about the time rate of change of climate change. Same goes for biological processes such as photosynthesis, in particular the response to water stress, which we don't know so well, which is very empirical. And that explains a lot of the spread we are seeing here, for instance, on the biogeochemical cycle and the carbon cycle. So basically at the end of the day, we have models that are relatively coarse and they have many, many processes that they need to represent in a so-called physically based way. But at the end of the day, those physically based parameterizations are really very empirical. And the hope is that we hope we can do a better job at representing them. And that's really the target of our new LEAP Center. So if you're interested, please feel free to reach out. So again, what is a parameterization? It's basically, we have a pretty coarse Earth system model. It could be at a different scale. But the main point is that you have a coarse model. And what you want to do is you want to represent the collective impact of small scale things, so physical or biological processes, and you want to represent their collective impact from a statistical standpoint, such as the impact of clouds on the mean climate. And again, typically those are physically based. We try to represent the impact in terms of some physical equations, but a lot of them, in fact, the majority of them are highly empirical, highly ad hoc, and there's very limited theory to actually explain those parameterizations. And in fact, we can argue that this is the main reason why climate models are so uncertain and why they disagree with each other is at the end of the day, because they have so much discrepancy in terms of the representation of those physical processes, in particular clouds or again, ocean eddy. Okay. And that really explains the intermodal spread in climate projections. At the end of the day, even though we are talking about long time scales and we are talking about very large spatial scales, you can actually relay those uncertainties to small scale processes that are relatively fast most of the time. So that's kind of the irony, but also the opportunity as well. So one thing I'll get started with is showing the potential to actually break that, or what we expected at the time, to actually break that deadlock and potentially using machine learning as a way to represent physically based parameterization and replace physically based parameterization. And the idea here is that, as I showed you before, high resolution simulations tend to do a better job, so such as for precipitation, and we could leverage those, right? We cannot run them forever. We cannot run them at the time scale of a climate model, but what we could do is we could run them for a couple of days, and we could learn from those simulations as a way to infer what should be done in a climate model. So just to give you a sense, you take some high resolution simulation here, you coarse grain that to a scale that's similar to a climate model. And once you have this coarse scale data, you can use your favorite machine learning algorithm, such as a neural network, and you can actually represent that as a coarse grain, what we call physics tendency. So basically how you should represent the physics in this model. So I'm gonna first show you some past successes, and some of the issues as well. And then we'll move on into how we can actually use that to get some better physical intuition and learn some new physics, because we're dealing with very large data sets. And so it's been a real trouble to extract physical insights and intuition based on those very massive data sets. So that's a study we started back in 2018. So, and the idea was, can we actually replace the way we represent big clouds, which we call convection, and precipitation in the models, because we know again that high resolution, a few kilometer scale simulations tend to do a much better job at representing precipitation. So what we did is exactly what I just showed you before. You take the high resolution simulations, every time and spatial snapshots, take all of that into a data set, coarse grain that to a scale that's similar to a climate model. And at this coarse resolution here, you have as an input some temperature, humidity, and wind data, plus some surface boundary conditions, such as evaporation. And we want to predict the rate of change over 2 time steps within the model, okay? And that's basically supervised learning. So we know exactly what should be the truth here. And we just frame that as a regression problem where we use a neural network here. So that was kind of the optimal model if you're interested in the details. That was actually able to make it work. So that was a deep neural network, and we got some pretty good success. So on the top left corner here, you can see the actual high resolution simulation. And here, NNCAM refers to the neural network emulated simulation compared to this benchmark here. And you can see that in terms of temperature mismatch, we have almost no temperature mismatch, even though here the neural network is fully coupled with the climate model. So we replaced the actual parameterization in the original model by a neural network. So it's fully interactive with the climate model. And you can see that we have really minimal biases, especially below what we call the tropopause here, but not in the higher atmosphere. Okay. If we compare that to the so-called physically based parameterization, which is this control experiment, so the control CAM experiment, which is the original parameterization, you can see that here you had very substantial biases and a double, what we call intertropical convergence zone. So very typical issue and very typical bias that we had in the model. So we are doing a much better job when we use a neural network, and that's comforting, right? It means that we are doing a much better job. And that's not just an average. In fact, you can look at individual snapshots as well. So the top is again the high resolution simulation. At the bottom is the neural network emulation, and you can see again we can even find, like in time and space, we can find pretty much all of the granularity that we find in the high resolution simulation at the top. We can actually have that as well in the neural network emulation. So that's great news. This is a slightly improved version. The first version just had what we call an aquaplanet, so just ocean. This one has land and ocean, so some of the complexities such as topography and the diurnal cycle over land. But overall, we are doing a pretty good job and all of the characteristics. And you could look at the distribution of precipitation. We're actually doing a much better job as well, which is basically one of the main points. Now, we have a couple of issues here. So the first one is actually, and that's when we started seeing a lot of issues actually, or some of the disappointment, I would say. So at the top here is a thought experiment of global warming in the high resolution simulation. So that's the baseline here on the left-hand side. We bumped the temperature at the surface by 1 degree, 2 degree, 3 degree, and 4 degree Kelvin. You can see the equatorial contraction, the pole world expansion, as you would expect. And then the neural network that was only trained on the historical climate was actually doing a terrible job in terms of the extrapolation. And in fact, it had the typical issue we are finding in the regular so-called physically based parameterization. It had actually also the double ATCZ, so something that was also not realistic. And basically we were back to the same type of issues we were having before. And we thought that's a major drawback, right? Because it means that even though we intended to use those models for projections, in fact, they are doing a relatively poor job, right? So it means that they are really not doing what we want. So it's not just an issue of generalization, which is one of the issues, but basically that's very typical also in machine learning. It's this out of sample issue because the temperatures in the future are way warmer than what we've seen in the past, right? So by definition, we didn't have that in our training data. We also had, as you can see here at the top, we are not very good at predicting the upper atmosphere here. And basically we believe that this is due to some spurious correlations because we are merging all of the data sets together and we have within the data set some spurious and artificial spatial correlations that maybe the neural network is actually learning by heart, right? And we believe that this was some implicit spurious correlation. And really at the end of the day, it's because we don't have causation in the model, we just have correlations, right? So that's a major drawback. A third issue that we found was an issue related to instabilities, right? So when you actually plug a neural network within a climate model, which is a pretty complex artillery, which is actually based in Fortran code, you actually try to plug something that was not really designed to work within a climate model. And typically you have a lot of bugs, a lot of instabilities, some temperatures that can go to the roof, that can go to like say 500 Kelvin. So unrealistic type of values. And that's because the model is unstable. So we did a fair amount of work trying to figure out how we could actually solve those instabilities, right? So that was an issue. And then the last issue is that we are not conserving energy and mass when you have a neural network, right? And kind of the interesting thing is that when we look at the neural network emulation here, and that's a column average energy energy balance, you can see that it's kind of interesting. We can see that the neural network kind of learned that there was an energy prediction, right? That there was some energy conservation, right? Because we're close to the one-to-one line, which would be perfect energy conservation. However, when we look around, there's quite a bit of departure from time to time. And in fact, we can get about 200 watts per square meter of departure, which is really big, right? Because climate change is just a few watts per square meter, right? So basically, it means that we cannot use those networks because they need to exactly conserve energy and mass, right? Because by definition, looking at climate change is a solid signal, right? In terms of an imbalance in energy at the top of the atmosphere. And so we believe as well that this was a major showstopper, basically, to actually use neural networks for climate change studies. There's a fix to that, so I'm just going to slightly digress for 1 minute. The energy and mass is less of a concern now for us because we believe we can actually fix that. And one way to do that is you have a neural network here, and you can actually add what we call constraining layers. So you can actually add a bunch of hidden layers at the end of your neural network, and you leave some degrees of freedom. So some of the neurons here are left basically unconstrained, and they are only constrained through this additional constraining layer. So think of that, say, one constraining layer will be energy conservation. The other one is going to be mass conservation. So you add 2 layers. You keep one of the neuron in the previous layer open, basically, so unconstrained. And you're going to constrain that value just based on the next constraining layer, right? So that at every time step, you ensure that everything is going to be fully constrained. And that's embedded within the architecture as opposed to regularization, where you could actually add as a weak constraint the energy or mass conservation, but it will not be perfect, right? It will just be close to that, but not exactly perfect. Within that architecture, you can actually conserve energy and mass within computing precision, right? So that's the intention here. Okay, so quick summary of where we were, at least a few years back now, when we started using machine learning. So it was really a roller coaster, that's the way I'm seeing that now. at first we were really excited. We could actually correctly emulate convection, which is a really big thing, like for quite some time, people were actually struggling with that. And we know that that's an important process. But then we realized that there were a lot of issues when using neural networks to emulate convection. So first of all, it was lacking stability. We were also missing some physical invariances, such as, and some physical conservation laws, such as energy and mass conservation. So that was a big no-no for us in terms of using that for climate study. But then kind of the more fundamental question is, what did we really learn, right? I mean, when you have a neural network with millions of degrees of freedoms and then millions of neurons, what do you really learn in terms of the physical processes of convection and what is actually driving convection? It's actually not that clear, right? And so that's why over the last couple of years, at least in my group, we've been trying to look at how can we actually also use machine learning to embed physical invariances. So I showed you one example here to improve stability and generalization. So we did some work doing some dimensional analysis to make sure we could actually extrapolate beyond the training data, but also trying to work with latent representations, right? So where you can actually work in a space that's much lower than millions of degrees of freedom so that we can actually better understand, and maybe better predict at the same time, right? So that things go hand in hand. So I'm going to show you some examples here, hoping that this would pick up your interest. So the idea here is that we start from the same kind of perspective as what we had before. We're going to have some high resolution simulations and we will want to learn things, right? We will want to learn some new physics. And we are going to do that by doing some sort of latent representation. And what we mean by that is we're going to shrink the dimension, right? On the input here, we're going to have a very high dimension. We want to shrink that to a much lower dimension. We call that the latent space. And then we could potentially what we call decode back, right? I mean, think of that if you've done some just basic data analysis, that would be a PCA. If you're doing it in a linear fashion, you can do it in a nonlinear way, just using a bunch of neurons and some nonlinear activation function. We call that a nonlinear PCA. That would be an autoencoder, which is, and then you could have some additional flavors like this one. Okay, so the first example I wanted to show you is actually based on what we call cloud organization. So we know that clouds are highly organized, and we can actually look at that in observation. So those are just some observations of cloud patterns here. And in fact, that was actually used as a benchmarking and a hackathon here, where people were trying to actually classify those different cloud types and then looking at different algorithms to automatically classify that. So that was a nice machine learning algorithm here. But the main point being here is that when we look at the subgrid scale here, like that's 200 kilometers roughly, we can see that they are very different patterns, right? So sometimes clouds are super highly organized as flowers, or they can be more diffuse as gravel, or they can have a different structure like fish, or also a little bit more homogeneous like the sugar here, right? So there's some degree of what we will call organization, right? And that's true in observations. It's also true in models. So we've been observing this so-called aggregation or organization in models as well. And sometimes if you run some simulation for long enough, so that's a high resolution simulation, again, of a few kilometers of scale. After some time, even though you start very random here, so this is some popcorn type convection, popcorn precipitation. You can see precipitation in blue here. You can see that after some time in some simulations, convection or precipitation tends to be super highly organized, within just one single cluster here, right? And the rest of the domain is actually very dry. But that region has pretty high precipitation rate, much higher, as you can see in blue here compared to the rest. And so potentially this degree of aggregation, which is smaller than a typical grid size in a climate model, might have a very substantial impact on radiation, right? Because there's a very big difference between the dry or clear sky radiation and the cloudy radiation. Also on accumulated precipitation, right? Because there might be a lot more precipitation here because we are sheltering the amount of precipitation, and also on the humidity profile as well, right? So on the dryness basically of the atmosphere. So that must be pretty important, and that's something we would want to basically understand a little bit better. And as I showed you before, so the way we typically parameterize precipitation and convection is to say that precipitation is a function of things we can resolve. And by that, what we mean is that we only have access to the average, the slab average, the slab average temperature or the slab average humidity, and we will need to actually try and predict precipitation just based on that. And kind of an implicit assumption is that we can actually do that, right? And that only having access to the core scale data is sufficient to actually predict precipitation. And there's been many schemes that have been trying to do that, you know, starting from, say, the Batson-Miller scheme back in the 80s, in 1986, which stated that precipitation was like some Heaviside function, some threshold that was temperature dependent, plus some sort of functional relationship as a function of the amount of water that you have in the atmosphere, right? So that makes sense. The more humid the column, plus some threshold, and then you will get some rainfall. And you have different flavors. People were trying to do that from a distribution standpoint. But at the end of the day, that's kind of the idea. You have access only to the core scale temperature and humidity, and you want to predict precipitation, and you hope that this works. Okay. But the question is really, do we need to include some more information, right, about the subgrid scale process to better predict precipitation, right? Is there something important? Especially, I showed you before, this level of organization. Is organization important to actually predict precipitation? That's kind of the question we want to answer here. So you could look at observations and again at those simulations, and again you can see the same type of pattern, right? So if you look at the average precipitation right here as a function of the integrated amount of water vapor in the atmosphere, you could see that there's kind of a nice parallel structure with some threshold that depends on the sea surface temperature here. And you could say it's actually very smooth, right? And it works really well. But those are long-term averages across many data points, right? So it's an average here across different beams of column water vapor. If we look, say, in models, because we have a lot more data points we can play with as opposed to a few radiosounds here, we can actually look at the stochasticity or the variability within a particular column water vapor bin, right? And you could say, let's say, if you have 60 millimeter of precipitable water, you can see there's substantial spread even for one given sea surface temperature, right? So you could say that's okay. We expect precipitation to be very stochastic, right? So there's a lot of like patchiness in rainfall, like things that can be pretty erratic. So for instance, here in Manhattan, for instance, it can rain uptown, it doesn't rain downtown. So we expect that, right? We expect some level of stochasticity. But the question is really, is it pure stochasticity, or is it just that we are missing some information about the subgrid processes, right? So that's the answer we would like to answer. So, and there's been a wealth of very interesting studies actually looking at this stochasticity. People believe it's actually really critical to include stochasticity in parameterization. And the reason for that is because it increases the variance, right? And that's presumably very important, especially for weather timescales. Could also potentially be for climate timescale and some modes of variability, but people believe it's actually very important, and we actually need to implement that in models, okay? And we'll try to link that to that, right? But really, what we want to do here is, can we actually improve the prediction of precipitation here by adding something? Let's call that stuff for now, right? And that's something we would like to define. So again, we're starting from this high resolution simulation, which is global, few kilometers in scale. And what we are doing as well is we are coarse graining that. We are coarse graining the data. We have the coarse scale field to the left-hand side, plug that into a neural network. So we have information about sea surface temperature, precipitable water, temperature, and humidity at 2 meters, because it gives you some information about what we call the boundary layer. You plug that into a neural network, and you're trying to predict the mean precipitation again over 100 kilometers, right? So this is everything here is happening at the core scale input, trying to predict core scale precipitation. And we're using this data, so we're working on the right-hand side to predict precipitation. And when you do that, I mean, this is the prediction here from the model, so in green. And you can see we can pick up this precipitable water scaling that we had before, right? So that's good news. It means that we have this kind of parallel behavior that we were seeing before and some sort of nice threshold as well. So that's very comforting. We can pick up kind of that behavior. Here on the left-hand side is just using precipitable water and sea surface temperature. In the middle is a slight improvement by adding some temperature and humidity at 2 meters. Overall, we get the same result, right? We can pick up the average behavior. I want to point out, though, that all of the blue shaded area here is all of the variance, so all of the so-called stochasticity I was showing you before, so the variability that you have within a particular bin, right? And we can see that the model actually here in green is not able to pick up that variability. And in fact, when we add the surface temperature and surface humidity, we can increase a little bit the variance. So we can pick up some of that stochasticity, but not a lot, right? So a lot of that is still missing. Another way to see that is to look at the precipitation distribution. So here is the high resolution precipitation distribution, which is doing a great job, very similar to the observations I showed you before. And here are the two predictions based on the coarse-scale neural network. And you can see that they are completely underestimating the extremes, right? And they have the same issue we had before. They are drizzling too much, right? So same very standard issue that we had in the physically based parameterization. So something is missing to better explain the extreme. So you could say maybe what is missing is some degree of organization, so something we could actually pick up from the organization. But then there's actually many studies on organization, and there's basically many definitions of organization. So it's not clear which one we should use. So there's basically a zoo of them. And so we thought like maybe there's a better way to actually assess that and to assess the degree of organization. So the whole trick, so that was led by Sarah Shamak in the group, is to say, let's take the high resolution. So every coarse resolution pixel here is going to have a high resolution precipitable water field, right? So it will have 32 by 32 pixels. And what we want to do, a 4 kilometer in resolution. And what we want to do is we want to say, can we encode some information into a much smaller latent space here and try to reconstruct the high resolution field, and also at the same time providing that information to the other neural network that we had seen before to best predict precipitation. And when we do that, so some of the tricks were to also include some translation invariance and some rotation invariance as well. So we embed that within the loss. And that's useful because we know that a cloud on the top right corner is the same as a cloud on the top left corner, right? So we don't want to have any impact of the location. And when we do that, we go from a size of 32 by 32, which is 2 to the 10, to a dimensionality reduction of 2 to the 2, right? Dimension 4. So dimension 4 could be interpretable, right? We can start thinking about what is the physics that we actually learned, right? So when we do that, so that's kind of the trick. We actually learn that, as we call it, end-to-end. We have a new neural network here that is ingesting, in addition to the large-scale data, it's ingesting the organization. And the organization is actually being fed at the same time by this encoder and decoder, which is this nonlinear dimensional reduction. And you're actually trying to learn that at the same time, right? So all of those, so both of those are actually learned at the same time. And we are trying to actually predict precipitation, right? So we are learning the organization, and at the same time, we are trying to best predict the precipitation. We're optimizing both neural networks at the same time. So on the left here, the encoder and decoder are two neural networks, and here we also have a neural network, right? So everything is actually learned together. And when we do that, so all of a sudden we can predict precipitation with very high accuracy. In fact, with an R-square of 0.8 on average, across precipitable water values. And you can see that we can really pick up the variance very well, right? So now most of the stochasticity that we had before, we can pick it up, right? Same when we go to the precipitation distribution, we can actually find that with very high accuracy as well, right? We can do a very good job at predicting all of the distribution of precipitation by including this subgrid scale information, right? So that's great news. It means that we can do a good job. And it's not just a time average. We can actually look at the spatial structure. So this is actually a map of the tropics. So here is South America. This is Indonesia here. And you can see in the baseline neural network that didn't include the organization, the R-square was close to 0, right? There's really no scale in predicting precipitation and the instances of precipitation. But we can do a great job when we start looking at organization, right? So all of a sudden, the R square is actually much, much higher, and we have very good skill, even on individual snapshots at sub-hourly timescale. So we are working at 15-minute times. So that's great news. So it means that we can actually learn some latent space, which is the organization. And we can, if we add that to our predictor, we can actually define almost a perfect prediction of precipitation, including all of what we called earlier the stochasticity. So it means that there's really no sense of stochasticity. It's actually more the degree of organization that's controlling the rate of precipitation. Now, the trouble is that we don't know this latent space a priori, right? And so we could say, how can we actually learn that, right? Because that's information about the subgrid. And so you could say we are cheating here because we actually know something more, right, that we didn't have access to, right? And you could say, but maybe what we could do is this latent space, we could learn it based on the large scale only, right? So we could predict this organization just based on the large scale. And basically, in a nutshell, what this is showing is in those 4 dimensions, it doesn't work, right? So it means that indeed the organization is more than just something that can be predicted by the large scale. So that's interesting. But a second option would be that you could say, okay, I cannot resolve the organization, but we could expect that to be a memory process, right? Because clouds tend to be highly organized in time and space. And maybe that's something that you could carry forward in time, right? And so that's what we did here with basically a simple autoregressive model with 4 time steps. And we can actually predict that really, really well. So it means that even though we cannot directly resolve that, we can actually represent it just as a very simple memory process that we could add to a regular parameterization. And that's basically good news. So it's pretty well, it works quite well. And it's also very practical for physically based parameterization. Now, the question is really, what did we learn? So when people look at those, what we call variational autoencoder, so those latent space, they want to learn things, right? So that's one example here, looking at faces, where people look at basically some autoencoder. So again, a dimensional reduction, and they can find that one dimension actually explains, you know, like the fact that you're angry or more smiley, and the other one is actually a pose, right? So you have 2 dimensions, one is pose, and then it's kind of angriness level, if you will. And you could kind of do the same in our latent space, right? So you could actually show that, in fact, when we look at 2 dimensions in the organization space, one refers to the degree of organization. So it's not exactly on those 2 dimensions, it's actually with a 45-degree angle. But one is actually the degree of organization, so the fact that clouds are more or less clustered. And the other one is more like the mean level of humidity. Is it more humid or not, right? So it means that we can start really investigating those latent spaces and to actually learn some new physics that we didn't have in the earlier model. So that's kind of great news. It means we can actually learn new physics. So very quickly to conclude, I would say we're also working on some other aspect of that, which is, can we actually embed? So I showed you one example here, which was we can embed some physical constraints within machine learning algorithms, but you could also say, can we really discover more than correlations, right? Can we discover causal mechanisms as opposed to just mere correlations? And the idea here is to say, in fact, most of the time we have to deal with time series, right? So you could look at different time series, and we could use those time series to actually start building a graph, right? And we call that basically a causal discovery algorithm. So here we're using the PCMCI algorithm from my colleague Jakob Runge. And the idea is to look at time correlations and to look at lags, you know, in the time correlation, to start emphasizing whether or not we have a causal relationship, right? And then you could actually prune the links, right? You could say, in fact, I can see that this edge or this node is actually causing this node here, and this one is actually causing this one, but we can prune the original one that was actually too strong, okay? And so what we did is we actually tried doing that within a neural network. So instead of connecting everything to everything, which is the case in the feed-forward neural network, we could say we can work on what we call a causal neural network, which is a very sparse neural network. And it's very much like dropout, right? You actually drop some of the connections here based on this causal analysis here. So you look at every single node, inputs to outputs, and the outputs are connected to very, very few of the inputs, right? So we create very, very, very sparse connections, and that provides a lot more causal perspective and also a lot more interpretable type of neural network. And we compare that to another neural network. I'll spare you the details here. So the main point is that we can actually get exact same skill, so that's again some snapshot here. So on the left-hand side is the high resolution model. In the middle is actually the fully connected neural network. And on the right-hand side is the causal neural network. And you can see it's barely distinguishable, the result. Same goes for like precipitation here at the bottom. So this was an average over the column, a time mean, but even on individual snapshots, we are doing very, very similar type of jobs. So it means that we can really find and get the same skill as a very, very deep neural network that had millions of degrees of freedom, even though now we only have like thousands. And also we can also build a lot more interpretability at the same time. And the other advantage is that now we are actually getting rid of the spurious correlations I showed you before. So by actually building in or imposing within the architecture this causation as opposed to this correlation, we can actually remove some of the spurious correlations, and we can remove also some of the instabilities because we had so many degrees of freedom that sometimes we would actually trigger things that we were not expecting, right? Because we have such a high dimension. It also very much limits the out of sample temperature prediction because all of a sudden we are building causation in the neural network as opposed to mere correlation, right? So we are doing a better job outside of the training sample because we are leveraging the fact that we know the causation and not just like some, again, a lot of correlation. So just very quick conclusion. So machine learning can do much more than emulating and curve fitting. It can really help process very large data sets to learn new things, right? We can actually build new physical understanding that was really challenging and challenged by the fact that we had to deal with terabytes and petabytes of data sometimes. And now we can actually, especially using lower dimensional representation in tandem with physical constraints, we can actually learn new things, right? And we believe that this is we are going to make a lot of discoveries in the future using those type of strategies. And there are many interesting challenges. So if we had a little bit more time, I'll be happy to talk about that. So some of that are related to extrapolating, right? Because climate change is all about extrapolating beyond the training data. And because we have non-stationary data sets or we only have sparse observations. So those are very interesting challenges for the machine learning community. We also have noisy and indirect and sparse observations, right? And that's also very untypical for the machine learning community where they have relatively well-specified data sets and relatively not unnoisy data sets. So that's kind of a nice angle to that. We also have a lot of work to do in terms of the interpretability. I showed you an example, but it's still pretty low dimension, like 2 to 4. But it becomes a bit more challenging when we go to high dimension, right? So there's still a lot of work to be done to better interpret algorithms, especially in high dimension, and when we have many variables at play. And then one of the last challenges here is that we also need to have proper uncertainty quantification, right? So typically, we don't want to provide just one prediction, where we want to provide some prediction or some product, or also providing some uncertainty quantification. And those uncertainties will depend on the state, and they also depend on which sensor we actually use, all right? So they are aleatoric, sensor, and epistemic errors, and we are also working very high dimension. And finally, and I'm actually very interested in that, is that the question is really that now we are starting to merge physical system with machine learning. And so we have a bunch of parameters on the physical side of things. So like here, theta of some physics, and we also have some parameters on the machine learning side. And we really need to actually train that or learn that together, right, using observation. So that's still a big challenge to how to know how to do that at scale. So with that, I'll be happy to take any questions. And if you have any interest or if you have any questions, please reach out. And we have this new center Leap, so feel free to visit our website. There's also a lecture series happening on Thursday, so feel free to register. Everything is hybrid. Thanks so much.
Thank you, Pierre. That was great. So now we can open for Q&A. So if anyone has any questions, you can raise your hands, type it in the chat, or unmute yourself. But we did have a question quite a while ago. They did have to leave, so I'm going to read this out loud, but they won't be able to respond to you, unfortunately. So here's the question. How should we tune the hyperparameters for predicting the missing data points for a nonlinear regression-based model for climate dataset? What type of deep neural model is efficient in this sector? I am working with mapping of missing data points for Greenland's ice bed.
Yeah, it's a bit hard to know without context, but there's a lot of work being done in terms of masking parts of images, and especially working with very similar types of approaches with latent representation, smaller dimensions, and then trying to extrapolate to regimes or parts of the domain that you have not seen. So feel free to be in touch with me, and I can point out some of those papers. So those are relatively recent from last year in particular.
Okay, thank you. And you have your email right on that side, so they'll know how to contact you. Does anyone else have any questions? You can raise your hand, you can unmute yourself, you can let me know in the chat. Dr. Lee, you can go ahead and ask it. Dr. Lee, I think we cannot hear you. In the meantime, while Dr. Lee gets he's unmuted, but I think his microphone is not working. We have a question from June in the chat. So the low dimensional presentation is actually further improving the physical parameterization?
Yes, by a lot actually. And so kind of the summary of that is what we believe it's saying is that we don't need a stochastic parameterization, which is a pretty strong statement, because we can actually just represent the degree of organization and we can really explain most of the stochasticity. And so it makes our life much, much easier because representing this stochasticity is very complicated and people have been working on that. And it's a very interesting problem in its own right, but it's very difficult to know what is the level of stochasticity, how does that depend on the state? And in that case, it's a very simple way to actually do that, yeah.
Okay, thank you. Julia, you can go next. And Dr. Lee, if you can't get your microphone to work, you can just, oh, I see a question in the chat. I'll ask it after Julia goes.
Okay, hi, Pierre. So I think this is a pretty basic question, but so you use training data to train your model. I was wondering how you're dealing with like long-term trends and, for instance, like increasing extremes and how you incorporate that if you're using your model to, do future simulations.
Yeah, that's a great question, and so that's basically the question we are trying to answer, and that was a lot of my frustration trying to use those high resolution simulations is because we don't have those trends, and so we try to play all sorts of tricks. The first one was very much inspired by fluid dynamics, trying to do what we call those dimensionless groups, so trying to collapse everything onto something we've seen, so people do that, they use what they call a Reynolds number, and that's really a way to take different length scale, different velocities, and collapse everything. We don't say that, but it's the same, like you're trying to collapse the distributions. And so that's kind of what we are trying to do, is collapsing all of the distributions and making sure that the distributions are not shifting, as you said. So we manipulate the data in a way, so we don't use temperature, we use temperature anomalies, so that's an easier way. We don't use specific humidity, we use relative humidity because it's always bounded between 0 and 100%, right? So it means that we will have some of that in our training data. And we also rescale precipitation, yeah. So that's, but that's still, I mean, we're working a lot on that, but it's still relatively empirical. We are trying to define a way to make it more, like, how can I say, systematic, but that's the heart of the problem. You're completely right? I mean, we want to extrapolate beyond what we've seen. Right. And in the models, you can play games. In the models, you could say, and that's what we did, we can actually simulate at higher sea surface temperatures. But if you only have observations, how can you predict the future? Right. And that's, that's been a lot of my interest over the last couple of years, trying to merge intuition or physics. And yeah, it's the question.
Okay, I wasn't sure, maybe you would come up with a solution.
No, not yet. I mean, we have some tricks and we have some work around there. I can put some pointers in the chat. Actually, we have one example.
Okay, cool. Thank you.
Dr. Lee, it looks like your microphone might be working. If you want to ask your question. Oh, it is not, unfortunately. We can see you, but we cannot hear you. I'll just go ahead and read Dr. Lee's question out loud because he put it in the chat. He said, while the oh my gosh, I'm so sorry. While the parameterization may not do as well as the NN, it is still valuable in understanding the physics. Can we use NN to generate any parameterization? And if you want to read that, it is in the chat.
Yes. So I'm not sure I understand the question, but yes, they are still very valuable. And so without like for movies, I'm just giving the trailer here. But we are working exactly on that. Like, can you work with merging regular parameterization that are not perfect, but that are building some trustworthiness along with all of the observations or the high resolution simulations that we have, and can we actually merge that in an efficient way? I think to me that would be potentially one way to approach that, and that goes back very much to the question that Julia had, how can you extrapolate beyond the training data? So maybe you cannot generate all of the training data, but you can merge things the right way. So that's very much what we are working on with Rose Yu at University of California, San Diego.
Great, thank you. Do we have any other questions? You can type it in the chat or raise your hand. Just want to give an extra second. Okay, well, in that case, unless I am interrupted, which please feel free to do so, I think we can wrap up today's talk. Thank you, Pierre, for coming and talking to us today, and thank you for everyone else for showing up today and showing up all the other semesters of this semester. See, oh my gosh, seminars of the semester. I'm clearly ready for a break, and I'm sure everybody else is as well. So we will resume at the end of January with our seminar season. Thank you, everybody. Have a great holiday season. Have a great break. Yeah, I will see you after in the new year.
Thanks for having me. Happy holidays.
Yeah, goodbye.